Welcome, microcontroller applicationistas. This will be our last lecture, and please, please hold your applause. All right. We're going to talk about control systems and Pid control systems and how microcontrollers can be used to implement them. So some of this material, I think, overlaps courses you've already had or are taking now, one or the other. But let's just kind of move through this and talk about what it kind of means, and hopefully it'll just kind of extend concepts you've already dealt with in your in building PLC systems and control systems in general. So the simplest control system is the open loop control system. There's no feedback in the open loop control system, and we talked about stepper motors, and as long as you don't exceed the load torque or the holding torque of a stepper motor, if you issue 15 pulses, the motor goes 15 steps, and you know where it is. You can keep track of that by counting the steps you go in this direction or that direction. And so you don't need any feedback as far as what the position is, and you can issue the steps at a certain rate to know what the velocity is. And so, there are lots of open loop control systems. You think about some kind of toaster that doesn't have any temperature control. You just, what you're really doing is maybe setting a timer, like a microwave oven, where you say, look, I want 1 minute of full power. And, it cooks the food for 1 minute, and then the bell rings. That's open loop. There's no feedback. Some of the toasters actually have some kind of thermocouple or thermistor in them, and when the toast reaches the temperature associated with number 5 on the dial, the toast pops up and that sort of thing. So there may actually be some kind of control in some of those toasters, but some of them are just a setting for how much current goes through the heater or how long it goes through. But you get the idea. There are some control systems that are, if you think about an automobile without a speedometer, you don't know how fast you're going. You just press the gas pedal and the car goes. The only feedback would be for you to watch the speedometer and limit the speed, or boost it if it falls too low. Whereas a closed loop control system would be cruise control, for instance. It can sense when the car is slowing down or when it's speeding up. And it keeps the car within a certain range of velocities, hopefully a relatively tightly controlled range of velocities, so you just head down the road at a constant speed. Another kind of control system that does have feedback is a threshold-based control system. The bang-bang control system. And it has a threshold and it has feedback. And so, you can imagine using, say, a potentiometer and, between two voltages to set a set point or a threshold, if you will. And maybe a temperature sensor comes back. And if the temperature sensor is less than the set point, then the comparator drives out a voltage to turn on, say, a heater relay, and this a heater comes on and heats up the area. When the temperature sensor comes back with a voltage that's higher than the set point, the heater relay turns off, and the room will cool down until this falls below. And that kind of a system is a bang-bang control system. And very common, and if done right, it can be pretty effective. Typically in a heating system, they'll make a couple of improvements. There might, for one thing, there's thermal mass out here. So you turn on the heater, the temperature rises over time until the threshold is crossed. Then the temperature falls over time, and then the temperature kicks on. And so, the furnace only ever runs 100% or 0%. So they call that a bang-bang control system. But the thermal mass of the room slows down the turning on and turning off, so it doesn't happen. It doesn't just sit there and click on, click off, click on, click off kind of thing, because it takes time for the heat to build up. And then, if there's any kind of insulation at all, it takes time for the heat to leave the system until it turns on. I don't know what you've had in other control system courses, but some people will actually, this is an important point, some people will actually build control systems such that the threshold to turn the system into one state is, say, higher than the threshold to change it to the other state. So that if you're in, say, state A, you have to go, there isn't just one threshold, there's actually two, and you have to go past the higher threshold to turn it on. And then for it to turn off, the feedback has to fall below the lower set point to turn it off. And this is just a way of preventing the system from banging on and off constantly at a high rate of speed, which is not good. And having two separate set points so that you can turn on in one direction and run for a while and then turn off in the other direction, and so that the system will operate in this way. They call that dual threshold system a system with hysteresis. And what's nice about a system like that is if there's some noise on the feedback signal, it won't sit there and bang the system on and off and on and off and on and off. The system has to go, above the threshold to go to one state. I should say it has to go above the higher threshold to go to one state and has to go below the lower threshold to go to another. So if the noise voltage coming back in your feedback is less than the difference between those two thresholds, the system won't be banging back and forth because of noise. The system will turn on when it considers the need serious enough to turn it on or go to one state, and it will go to the other state when it considers the need serious enough to go to the other state, but it'll create a little distance in between the two. Again, that's called hysteresis. And I don't have it in this document, but you can look it up. It's a concept. You see, it can be provided in the 555 timer. If you think about the 555 timer, which I'm sure you've looked at, it has 3 5K resistors in it. And they create two set points, one at 1/3 of the supply voltage and the other at 2/3 of the supply voltage. Because there's 3 resistors of equal value, as a voltage divider will create two junction points there, one at 2/3 of voltage, one at 1/3. And you can create a system using the flip-flop in the 555 and those two thresholds. You can create a system that has a third of the supply voltage of hysteresis. In other words, you have to go above 2/3 of the supply voltage to put the flip-flop in one state, and then you have to go back below 1/3 of the supply voltage to put the flip-flop back in the other state. And this is, if you use capacitors and resistors, this is how you can build astable multivibrators, that is, kind of oscillators, free-running oscillators. You can build monostable or one-shot circuits, and you can build bistable or two-state circuits. But most importantly, with hysteresis, you get two thresholds with the 555, one at 2/3 of supply, one at 1/3 of supply. In other control systems, you may find that there are two thresholds, both near the effective threshold you want, but one's a little higher and one's a little lower, and it's just to avoid the noise or chatter that might happen if there were noise on the feedback circuit. So that's a bang-bang control system. If you think about something like this could be done with an analog comparator, and has been done that way. With an analog comparator, there are circuits with some feedback resistors where you can even create some hysteresis if you want. But if not, you can build one that has one single threshold if you like. And as you can imagine, this is not hard to do with a microcontroller either. So a person can have the set point come into an analog to digital converter on a microcontroller, and the microcontroller can look at say a temperature sensor or some sensor which comes in on another analog to digital converter input, and mathematically compare the two. If the top one is higher than the lower one, then maybe it puts on a signal to turn on a heater relay, or does whatever it does to put the system in one state. And then if the mathematical result is not that the set point is higher than the feedback, then it can put the system in another state. And it would be pretty easy to include hysteresis in there by having two such thresholds. And you could also come along with some kind of device and talk to that microcontroller and say, hey, we want to change the set points. We've used this system in one way. Now we want to fine tune it and change those set points so we can use it in another way, or just the material, the temperatures or the pressures or whatever it is, are something we want to be able to change. So with an analog system, you'd have to do that with potentiometers and that sort of thing, and they used to do that, and they'd put some kind of this Loctite used to make, still does I guess, it made this goop that you could put on trim pots to do two things. One, keep dirt out of the trim pot, hopefully, and number two, just put an added kind of stickiness there so that the trim pot didn't change in value over time. Microcontroller, it brings programmability, and it could even bring in some test features and that sort of thing to a bang-bang control system. You could put in your own kinds of hysteresis if you wanted to, and diagnostic functions and that sort of thing. That's great. That's one of the first kind of systems we come across is the bang-bang control system. But it doesn't take too long before we have to deal with the generalized continuous control system, and that looks kind of like this whiteboard diagram. In here, let me make the screen a little bigger. In this kind of system, you have a command input, and let's pretend this is all an analog system, and we haven't talked about microcontrollers yet. You'd have an analog voltage coming in saying, I want the system to do something to a certain degree, and then you have feedback from the output, and this G and H block, they're just they're filters to maybe get rid of noise or do whatever else is necessary. Maybe some gain here to turn, to drive an actual motor or something. But whatever the operating control system is, there's typically some kind of plant and drive in the forward direction to drive the output based on an error voltage, and some kind of feedback, typically with some kind of filtering or maybe compensation or whatever's necessary that comes back. And then we compare these two, and sigma just means sum. All right. So what this is like a difference amplifier, really. If this were an analog circuit, it would be a difference amplifier, and we'd say, V in of t minus V FB or V feedback of t equals V error of t. And that error signal would go in here and help us figure out what we're going to do to get the system to be where we want it. And that's this whole idea of servo systems. And servo, in a generalized manner, means some kind of system that you can command basically a system that you can command, and it affects an output or a result that is that your input is asking for. If you want to move a crane up and to the left, you'd have inputs where you can say, I want to raise the crane, I want to turn it to the left or to the right, or that sort of thing. So one of the classic things is the servo motor, which is a kind of a DC motor driven by an amplifier, and there's some circuits so that you can position things. You drive the motor to a certain point or position, and that's used to control some process or whatever. And there's feedback, so that the feedback helps you do things like, look, I don't want to overshoot where I was going toward, and the feedback could tell me, you're getting close. Why don't you back down the drive a little bit so you can kind of come in close and stop, just like landing an airplane or parking a car. So some generalized ideas about these kind of control systems. This red VN, if you come along with, starting at 0 voltage and you go, well, typically 1 volt would be the unit step. You come in here and you immediately at time 0 go to a certain value and say, how does the system respond to that? Because that tells us a lot. And if the system responds by going past there and then having to come back, and it overshoots too far, and then it goes up and it overshoots and eventually it gets into some acceptable closeness to the target, that system is underdamped. It's just too responsive. I mean, you could think of an old shock absorber that's kind of worn out, and you hit a pothole. So the pothole is kind of a step down and then a step back up. And what happens to the suspension on the car, you feel like you're riding the waves for a while. The car is up and down and up and down. And so that is underdamped. It's overly responsive, causing excessive overshoot and a long settling time. Now the opposite of that is an overdamped system, and that's this other green curve here, that you get the input unit step and the system says, okay, I'm going to get there eventually, and it moves very slowly and finally gets within an acceptable range of the commanded input, and that may take a long time. It will be a sluggish response, but there's no overshoot. And if you were steering a ship in the Suez Canal, you might be willing to have some over damping in your response. Of course, if it's really over damped and you would put too much left rudder in, it might take too long to get back some right rudder, so it could be hard to correct, you know. So you can imagine control systems, well, this is why we talk about them. And then there's another type of control system that's critically damped, and it responds as quickly as possible without overshoot. So you have the red step input here, and the critically damped system does, you know, it responds. It won't respond as fast as the step input, but it responds at a decent rate, and it comes up and it just you know, hits the target output, and it doesn't overshoot it or undershoot it or anything, and yet it goes about as quickly as you can without that overshoot. So the kind of control systems that are often talked about in terms of this kind of thing, because they're so successful, there are these the control systems you study in a 4-year college. You start off with what are called generalized second-order control systems. Don't even worry about what that means. It's just that those control systems tend to be characterized by 3 numbers. And they'll have a damping factor and a natural frequency, and usually a DC gain. Another way of characterizing those control systems with 3 different parameters is what's called a proportional integral derivative, or PID, PID or PID control system. And so it's just another type of this second order control system. And second order control systems capture a lot of these 3 behaviors here. Critically damped is just great. You know, underdamped gives you a lot of kind of ringing or overshoot. And then overdamped gives you that sluggish, sluggish response that can be bad when you're can be just as bad in trying to turn a steamship as the underdamped response. So, but so proportional, integral, and derivative control systems are differential. A proportional control system works by driving the system in the direction of the error voltage in a manner proportional to the error voltage. So here's a proportional system. You got a command input, you got a feedback, and then you have some gain. And, you know, the bigger the error, the more oomph to try to get you there. And, you know, this is actually a pretty effective control system in a way. But the one problem is that if the gain is really high, this system will overshoot, then whip back, and then whip forward, and then whip back. So if this drive system it has too much gain, it'll take a long time, and it can even go unstable in some circumstances. So the output will be just searching back and forward. And if there's not if you don't have that situation, you could well have the situation where, as the error voltage gets small, the proportional factor times the error voltage is just not enough oomph to really get the thing to finish out. So one characterization of these proportional systems is they get moving nicely, but they have a tough time finishing the job, because as you get closer and closer and the error voltage gets small, then even with this gain factor, you may not have enough oomph in the system to finish. So along comes the integral factor, and it adds another feature. Integral control remembers the recent errors in the control system. So if you look at the proportional control, when it when it's done a lot of its work, the error gets small, and the proportional factor here has a tough time driving the system to finish out. The integral system remembers, it adds up, it integrates recent error, so that if the system had been closing in on a target value, and the proportional drive to get it to finish was pooping out, well, the integral could say, hey, I know you've still got some distance to cover, and as a factor, I will add some oomph into the system, and we'll finish out. So the integral remembers history in the system, and uses the memory of that history to say, hey, we've still got more work to do. I remember us being behind the 8-ball. Now, this proportional system has, K sub P as a constant. You multiply that by the error voltage, and it gives you an amount of drive. And so they call it proportional. In integral, you add up the history, the error history, and you multiply that error history by K sub I, and that will add in some more correction. And proportional integral systems, so we had the P system, now we have the PI system. They can be quite effective. They're, a lot of temperature control systems will be proportional integral, because proportional itself may get you close, but you might not, really get the temperature exactly where you want. So the integral system, with its remembering of recent history, can help the proportional system by saying, look, I know we've got a little bit more error that has to be overcome, and so with its separate constant, the K sub I, it'll drive the control system to finish and hit the desired temperature. The last factor, so we have PI, proportional integral, and differential. The idea of the differential system, as you can see, here's the proportional. We have a constant times the error voltage. Here's the integral. We have a constant times the sum of the previous errors. And then we have the derivative, in which case we look at essentially the rate of change. We look at the change in the error signal. The previous error minus the current error. We multiply that by a constant because we may want to tell the system it's okay to go very aggressive when the proportional, when the error is large. But when the error gets smaller, or the rate of change of the error gets smaller, we may want to, move back the response of the system, or just the opposite. When the system, is commanded to move very quickly, we may want to tell the system, look, we don't want you to go too awfully quick because you might overshoot. So the derivative system kind of looks at the rate of change of the system and helps to put brakes on if the system is moving too awfully fast. And with that factor, you can see how the system could have, damping and act like a classic second-order system that has a constant called the damping factor. So for many years, PID controllers and similar feedback control systems were implemented in analog circuitry combining op amps, resistors, capacitors. Actually, before op amps, they built op amps with tubes, and control systems were built with tube circuits, and they worked quite well. In World War II, a lot of early control systems were built using vacuum tube operational amplifiers, and they were able to build closed-loop control systems for steering radars and aiming guns and, you know, controlling rudders and all that sort of thing. So lastly, we get to the point of talking about a microcontroller-based PID control system. So I think you've heard a lot of this before about PID, how it has proportional, integral, and derivative control system. Here's a diagram of us taking that PID system and putting it, together, putting it into a microcontroller chip. So where we have a command input, that command input may be analog, and our feedback may be analog. Not always that way, but if they are analog, we can use analog to digital converters, which on many microcontrollers nowadays are available built right onto the chip. So we can get our analog controls, inputs, converted to digital. We can do this, we can create this error voltage as a matter mathematically of subtracting the command, subtracting the feedback from the command, coming up with an error. And then what we do is we, for instance, in a control system I've often used, made by Galil, Galil, it's a motion control system. They sample these inputs 2,000 times a second, so every half a millisecond, and you can get some that goes like to 16,000 times a second. But basically in each half a millisecond they get a new reading, and they compute P, I, and D. Although so they compute these things. You get to set what KP, KI, and KD are. They compute a new output, and that output can be driven. In the system I used, it was actually a PWM output. It was driving a brushed stepper motor, and so the PWM output drove a motor amplifier that had an H bridge in it, and the PWM output was a 0 to 10 volt system, and the duty cycle or percentage of on time gave the effective voltage between 0 and 10 volts for driving the motor. And there are systems that do the same thing with minus 10 to plus 10 volt systems, where they're bidirectional, or they may even have a direction wire and go 0 to 10 volts. And there's a lot of other systems too. You don't even have to convert this to analog or PWM. This might be a command that then goes to some other box that does the conversion. But the PID algorithm, the computations for it, are done in the core of the microcontroller, and the peripherals around the microcontroller, be they digital to analog converters or PWM outputs, and analog to digital converters for your analog inputs, allows you to implement a fancy control system on one chip. So I'm just mentioning here that if you think about the PWM, back when we were doing, I think, the freak out or one of those synthesis functions on the basic stamp, we used PWM, put it through a simple but effective low-pass filter, and we got a sine wave out. And we even put that sine wave through a speaker and change pitches and that sort of thing. We did that with our basic stamps. So that's a summary of just basic control systems and where they've come from in terms of analog systems with op amps and resistors and all that stuff on boards, and maybe even trim pots to try to tune them or tweak them, to microcontroller embedded systems where one can hook up a cable or a CAN bus or I2C or SPI or serial or something, Ethernet, and talk to the thing and program it that way. Ethernet was what I was using with the Galil. One of them was on PCI on a computer, the other was on Ethernet. So let's talk a little bit about some PID stuff. I think, and that'll be our wrap up. We have, let me get the right directory here. I found a PID simulator that I thought worked halfway decently. It was at Carnegie Mellon University, or CMU as they're called, and it's in an Excel spreadsheet, and I have posted the URL for this on the Blackboard site. But here's a controller. Now, they're simulating a PID controller. You can see KP, KI, KD, and that's all great, but they're simulating it for a system that has some mass and some, I don't know, it could have an initial velocity if you wanted to, but there's a system here that they're doing it. So these PID or KP, KI, and KD numbers are not universal. They're going to behave a certain way with this system. So in this instance, proportional is 3, integral is 0.8, and derivative is 0.7. And you can see this system, which starts out at initial position 1 and is supposed to go to target position 10, has just a tiny amount of overshoot. It comes back and then it settles out in a certain amount of time here, I guess 3.5, 4 seconds. And that's not a bad behavior right there. That's pretty good. Now you may have to be conservative. Maybe no overshoot is allowed because your system has hard stops or something like that. If that's the case, you'll design your system for that. Here's a couple examples. Here I put in a proportional constant of 1 and no integral or derivative. And you can see this system just sits there and oscillates. It shoots past the desired set point. It comes back, to here, and it just sits there and oscillates back and forth. Some people will call this hunting. The system is hunting for a solution. So here's an example where without integral or differential control, this system is not going to be stable. It's not going to converge on an answer. So I'll try some other cases here. Here's a case where it's even worse. I have the proportional control and I have some integral control, so I'm willing to remember some of my error. Well, if my system was so overpowered proportionally that it was unstable or it was hunting back and forth, as you can see, the integral term remembers this error and tries to correct for it, and the system hunts worse and worse and worse. So that's not good. So PID systems aren't automatically stable. They have to be tuned for stability. Let's look at some other cases here. Now here's a case, remember we had something like 3.8 and 0.7 and had a decent response. Here's one that's not too awfully bad. If you can stand a little overshoot, we've got a pretty healthy gain here. Apparently this input is moving quite quickly, and I think it knows it has to slow down, but it can't help but overshoot to about 11, so it's about a 10% overshoot. Not the worst thing in the world. and maybe 11% overshoot because I started from 1. And it comes back and it undershoots, if you will. It's not really, I mean. But then it kind of gets itself converged and stays right on the target. So, you know, when you use all 3 parameters, it's possible to tune a system to behave like you want. So if you don't mind a little bit of overshoot and you want to get the system moving quickly, you know, you could let your proportional term be a little bit aggressive and, you know, kind of fix things up by remembering history and by you know, having a little bit of, you know, velocity feedback there, if you will. That derivative term will kind of let the system know that it is moving quickly. Here's another one. Now this one, I don't know if this one is critically damped. Probably not. This system's probably a little overdamped. But you can see here, we have a real strong gain of 16 to move this thing pretty quickly. But we also have a pretty strong velocity component here. This derivative component sees that it's changing quickly and says, hey, you know, let's not, you know, let's not overshoot this thing. You know, let's not go too fast. Let's not let inertia get the best of us and swing past this thing and have to come back. So as it gets close, it sort of you know, noses over and just hits it beautifully. And there's a little bit of integral term there to remember this error, so we do close all the way into the target value. But also because of the oomph we have and because of our caution on the overall velocity, we wind up with a nice system that converges and does not overshoot. And lastly, this system once again, you look at these terms, and now here we're at 1, and before we saw that 1 overshot a little bit when we had and we had 0.8 for the integral, and we had 0.7 for the velocity or derivative input. So 0.7 we kept and 1 we kept, but we backed off the integral error a little bit. And you can see here that we swung up here. And there's the slightest overshoot, and then we can back down and everything's good. If I were to take you back to, is it this one? Nope. Now that one's better than I wanted. I guess I have to go to this one. There we go. Here's a 2.1.5. It moves very quickly, but it also has some overshoot. The neat thing about the system we were looking at, you know, there actually is some overshoot, but it doesn't move as quickly, but you know, it performs nicely. It's got good behavior. And then we had the one we had before that. This one, yeah, this is the best one I've seen. You know, kind of tune these parameters a little bit, and that's the best performance we could get. So, you know, that's the effect of using this proportional, integral, and differential system. And there are tuning algorithms out there, and you may even have used them in labs or whatever. But I just wanted to, you know, review the idea of a second-order control system, especially from a PID standpoint, because they're so popular. They're quite well understood. You can you can run them on Arduinos, you can run them on basic stamps, you can run them on all sorts of machines. They're built into PLCs, and they're a good generalized controller. And you can always, if you don't need one of these factors, you can always set it to 0. So that is it for lectures in spring semester 2021 of EET 260. Thank you very much for listening to all my babbling, and we'll be posting a final exam, and some of this material will be on it. Okie doke. So take it easy. Best wishes in all your pursuits, and it's been great yakking into this box for the semester. I hope it has helped and has brought some insight into how microcontrollers are used, and how they permeate everything from thermostats to Apple Watches to PLC controllers to motor speed controllers to everything else that's in the businesses you guys are in, and that you can appreciate them and put them to use, and and make some money in doing so. All right, have a great rest of the semester, and thank you again. All right, bye-bye.